Welcome to Ask and Learn.
Okay, so for this one, you have the electric field and you want to find the charge distribution. And then you know the electric field is k r to the fourth. And then the goal is to get rho. So we know that the problem says that rho is radially symmetric. And so we know it's going to go as like r to some power. And so we know that we can write rho, therefore, as some constant times r to the n. So then our goal is to solve for c and n. And we can do that using Gauss's law, which relates generically relates electric fields and charges. So you can say that E, so again, with Gauss's law, with spherically symmetric distributions, we can say E times EA. Okay, the integral of E dot dA is Q enclosed over epsilon naught. E dot dA, the integral of E dot dA is E times 4 pi r squared. And then Q enclosed is going to be the integral of rho dV over epsilon naught. So let's kind of work through this side of the equation and just do the integral. And so plugging in for rho, we can say it's C over epsilon naught times the integral of r to the n. And then dV, our differential volume element, is r squared dr times 4 pi. Again, because I've said it in many of the other videos, that's the differential volume element of a sphere, which you've hopefully seen in a calculus class. And so evaluating this integral from 0 to some r, I obtained that it's c r to the 2 minus n plus 1, just using the integral rules, 2 minus n plus 1, all multiplied by 4 pi. And so if you take this and we plug it in, well, we already have it plugged in. Okay, and then now working in this left side, this E is kr to the fourth, and so this is going to be k r to the fourth times r squared is r to the sixth times 4 pi. Oh, and so lovely, these 4 pi's cancel. And so we're left with, what I have written there. And so let's just simplify it a bit. So simplifying this, we can write it as k r to the sixth is equal to c over epsilon naught times r to the 3 minus n, and then divided by 3 minus n. So looking at the r's, we can see that we definitely need these to have the same powers in order for these to be true for any r. So then therefore we can conclude that n has to equal -3, because 6 equals 3 minus n. And then the coefficients have to be the same too, so we can say, we can say that c equals epsilon naught times 3 minus n. And then we said with n was -3, so then c is equal to 6 epsilon naught. And therefore, the total charge density is 6 epsilon naught times r to the -3rd. Just going to double check that. I just want to double check that sign. 3 minus -n has to equal 6. Yeah, so n has to equal 3. Oh, whoops. Let me go back, actually. So, yeah. So actually, let me go. I'm going back to the first one. And so it should actually be 2 minus, not 2 minus n, but 2 plus n. Because it's n plus 1, or n plus 2 plus 1. Okay, great. I'm glad I found that mistake. And so this becomes a plus. I'm just used to fields going off as like 1 over r or something, but I guess it should, if the charge intensity is growing, then, or if the field is growing, so should the charge intensity. So yes. Yeah, and then that should be 3 plus n, but that doesn't change that. So then it should go like that. Okay, awesome. I'm glad I caught that mistake.